Good afternoon, everyone. I hope you are doing all right. And if you still remember, we had midterm last class, and those scores, including the clicker scores, they are already posted on Canvas. I'm sure you have already seen it. Just in case, if you haven't, it is there. So we started talking about charge, and then we talked about how charge creates field, and there are going to be force between two charges, and we can describe interaction between charges like in terms of force, or also we can describe in terms of energy or even potential energy per unit charge, right? And then we talked about moving charges that makes current. So we talked about current. So basically that concludes the electric field. So today we're going to start talking about magnetic field. So electric field and magnetic field, they may seem like, in some aspect they are similar, in some aspect they are different. But if we go to the root of the magnetic field, basically the origin of that field is also moving charge. It's not just charge, but moving charge, okay? Remember how we counted, okay, what's the rate of flow of charge as a current? But here we're going to be talking about, okay, if there is charge moving, it produces magnetic field just like a magnet does. Okay, so that means the surrounding around it, we have a charge, and near the charge, if we bring another charge, that charge experience force. Similarly, when we have a magnet, and if we bring another magnet near it, what happens? It experiences that force. So there is field around it. That's what we say it. Okay. So that means we have a field around this magnet. And to visualize that field, just like we did in case of electric charge, now we can draw magnetic field lines. Okay. So this is electric field line. To be more accurate, we have one charge positive, another equal and opposite charge. They are separated by a certain distance. That kind of configuration we learn that it is called dipole. So similarly, magnet also have two poles, north and south pole. And what happens here? The main difference between these field lines is that for the charges, the field line starts from positive charge and just ends at the negative charge. But for the magnet, what happens is it starts from north and then comes to the south, but it just does not end there. What happens? You see here, goes all inside as well. So there is field line between the poles as well, north and south, and inside is going from south to north, if you notice that there, okay, inside that. So it makes a loop, it forms a loop. This is, I should say, closed loop, okay? So it may look like a loop for these as well, but it's not a complete loop, closed loop. But in case of magnetic field, we have this closed field line and other properties. For example, how do I find the direction of electric field? From field lines, we draw a tangent line. We can do the same thing for the magnetic field. And by the way, we denote magnetic field by uppercase B. Okay, just like electric field, we denoted that by uppercase E. For magnetic field, we denote that by uppercase B. And of course, this simply means that magnetic field is a vector quantity like electric field. Okay, so that's the main difference between electric and magnetic field lines. Oh, looks like I did not post the class slide, huh? Okay, then give me a second. Okay, so these are the field lines of single charge, positive charge and negative charge. For positive charge, field lines, they are getting out. For negative charge, they are getting in. So they can independently exist, okay? But let's say if I try to say, okay, there is north and there is south, like a positive and negative charge, this kind of thing is not possible, okay? So just like single charge is possible, single pole is not possible. Single pole of magnet is also known as monopole, okay? So we call that, okay, magnetic pole does not exist. Both poles kind of rises, simultaneously. Both of them gonna be same. So now, then why? What's the reason then? Why cannot we have just North Pole or just South Pole, right? The question arises. So to answer that question, we have to go and look at the origin of the magnetic field, okay? How the magnetic property of material arises, okay? So if we keep breaking this magnet, what happens no matter how small we break, we're going to have north and south pole right there. So there is south and there's going to be north pole there. And this is going to look like this, okay? So every piece acts like both poles, okay, no matter how small it is. So if we keep breaking and go to the all the way to the, atomic levels, so in atoms, what happens? There is a nucleus and nucleus is positively charged and there are electrons orbiting around, okay? So what happens is even if we were to go to a tiny, atom, it's of course that's not possible to go to exactly in one atom. But let's say if we were to do that, then we'll still find north and south pole. So for example, as long as we have one electron, and every material, remember, has positive and negative charge, right? So the electron, even if we have a single electron, it acts like a electron is moving. So it acts like a loop of current, okay? And then what happens? You notice there is this magnetic field lines going just like in case of magnet, okay? So that's what we notice. So that means it turns out that even a single electron generates both north and south pole. Okay, so this is magnetic dipole of an electron, let's say. Or if we are looking at, it's not possible to isolate electron, so we may say, okay, it's a atomic dipole. Okay, and so that's why we cannot have just a monopole. So now, okay, I said, okay, they're going to be north and south pole, even for a loop, even for a single electron, if it is going around, it acts like a current loop, and we can have north and south pole. But how do I know, north pole is there and south pole is there? So for that, we need to figure out, okay, which way the current is flowing, okay? Here, this is not the direction of flow of electron. Remember, direction of flow of electron is opposite to the direction of flow of current. That's what we call conventional current. We talked about that, 2 classes ago. So here, this current is going something like this. So if we look from the top, it is going counterclockwise, okay? So if I look from here, this side, it is going counterclockwise. So clockwise and counterclockwise depends on which side we are looking from. So we have to be a bit careful. So for example, I have this loop here, okay? So if we look from this side, then if we go like this, that's going to be counterclockwise. But the same thing, when I look from my side, what happens? It becomes clockwise, okay? So which side we are looking for becomes important. Unless there is obvious, okay, there is only one side we can look from. Otherwise, we can be looking from the top, could be looking from the bottom, right? So which side we are looking for from. So when we look from this, uh, upper part of this loop, then the current is going counterclockwise, okay? So in that case, how these magnetic field lines are coming and going. So if we, like if we were to make that little bigger and remove a bit more mess and add some useful information, this is what we're going to get. So what happens is the field lines are coming out from inside the loop. And they are the circling. And then it's circling. Okay, so it's going around like that. So it's coming from, let's say if it's going counterclockwise like this, the field lines are coming out like that, and they are going and coming in like that, okay? And so to denote in 2 dimension, we may also use this notation. So when we see this, tip, so think about arrow. So when we are looking at here, it's like looking at this tip of the arrow. So it's like coming out. And this is like it's the back of the arrow, like cross, okay? So that means if we draw something like that, that means the field is going inside in this plane, for example. Okay, so I'm drawing this in 2 dimensions. So field lines are coming out and going in and circling like that. Okay, so hard to visualize and becomes messy. So we do something like that. Okay, so there is a question on the chat. So what exactly do we mean by dipole? So dipole means 2 poles. Di means 2. So magnet has north pole and south pole. We call that dipole. When we have charge positive and negative sitting or separated by a certain distance, it's like one pole. This is another pole, dipole. Earth also has a dipole. Earth can be thought as a dipole. It has north pole and south pole, right? If we have only one pole, that's going to be monopole. And in case of magnet, that does not exist. So that's what we talked about. Okay. So here, to figure this out, what we do is like, okay, so how is working out? So for that, we use right-hand rule. Okay. Right-hand rule. And there are 2 different kind of right-hand rules. So let's pay attention and learn both of them. And if you search right-hand rule online, you may find several versions of them, okay? So let's stick with what we do here in the class. And I think this is, once you learn, this is gonna be the easiest way to, remember and figure out, okay? So what do we do is, this has to be right hand, okay? And then you start by stretching these 4 fingers in one direction and then thumb perpendicular to that, right? So we can stretch something like that. So free up your right hand and then stretch like that. Let's begin with that, okay? And then now what we want to do is we want to crawl these fingers. So thumb is still stretched, but now we want to crawl this finger. See how I am crawling here? But which direction though? So it is in the direction of flow of current. So for example, if you have something round object like this in your home, right, you can use that. And so you can wrap like this. So these four fingers, right, and this thumb is being stretched. So in this case, yes, video is tiny, but probably you can still see it. And so what happens? The thumb is pointing up right now when I'm curling my finger this way. Now, if I were to go other way around, let's say clockwise, then how do I orient my hand? So I need to flip my hand, and now thumb has to go down, right? So if current is going clockwise, then it's going to be down in this case. And when current is going counterclockwise in this particular case, it's going to be up. So now if it is like, let's say vertical, if it is in a vertical plane, then we can do the same thing. So for example, if the current is going like this, I can crawl my finger in the direction of current, and then now thumb is pointing towards me, okay? And if the current was going all the way around, then that I cannot crawl my finger backward, right? So the palm kind of goes towards the current, okay? Palm goes towards the current, so that's how we can carve it, okay? So this one gives the magnetic field, okay? So here is a question. So here I'm saying, so, this look could be sometimes deceiving. So this is the farther side and this is closer to us. So if I am holding something like this, what happens is one side is farther from me and another one is closer to me. So that's what I am saying, okay? So that way we can tell which way current is going here. So when looked from this side, it is going counterclockwise. So if that's the case, what is the direction of magnetic dipole or the magnetic field, right? What's the direction of magnetic field or magnetic dipole in this case? So I'm opening the pole. So go ahead, use your right hand and pretend you are orienting, looking at the picture, and then choose answer. You have a minute and 30 seconds. So everyone, please free up your hand and maybe grab something like this, or it can be ball. You can also grab a ball, right? So think about the ball and current is going something like that. So you can grab a ball like this or like that, right? Anything. You can roll a piece of paper and then roll your finger over the piece of paper. Oh, 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got B and D mostly, but there are A and C as well. Hey, B and D split. So did you stretch your hand? Remember, the finger has to be curling this way. So goes like that and coming something like that. Okay. So here in the zoom it's a bit difficult because video gets image gets flipped. Okay. When I zoom with my hand. So you have to actually do it looking at the diagram. Okay. Here. So here my finger is flipped. It shows that way. Oh, okay. So anyway, so in this case, when I crawl my finger this way and I stretch my finger, sorry, the thumb, my thumb points this way. If you did not get that, try one more time. Okay, the fingers going like that. So you may have to, roll your hand a little bit and so that you can carve it. Okay. In this case, D is correct answer based on this diagram. And I was also checking the chat. I don't know why it's not letting you to write to everyone, but seems like I have set up this to, let's say, do the everyone. Okay, so that's that. So are we good here? So we're going to be using this intensively in this chapter and the next chapter. So make sure become fluent. So when we move to the induction next class, next week, we need, this is going to be the very first step we're going to be using in many cases. Okay. So now, let's say we can think okay, there are so many atoms, and that means each atom is producing a magnet, a magnetic dipole, right? So we can think of something like that. But how come we cannot make, how come we cannot make a wood a magnet? Have you seen wooden magnet? The magnet has to be always mostly iron, cobalt, nickel, okay? Other elements like iron, steel, aluminum, those things you cannot make magnet out of that. What's the reason, right? So it turns out that in case of those materials that we cannot make magnet, what happens is one tiny magnet from one electron and another tiny magnet from another electron, they are orienting exactly in opposite direction and they cancel. Okay, so the net effect is zero. But for the iron, cobalt, and nickel, that kind of metals, what happens? They form a domain. That means a small area inside the metal where they line up in one direction by themselves. So you can see here, there is one in a small area. This is the magnetic field is oriented this way. And another area, we call that domain, okay, domain. So it forms this tiny magnetic domains, okay. The domain is here. And then but what happens is the iron itself is not always a magnet, but we can make magnet out of iron. So how is that done? So why it's not a magnet? Because their orientation is still random, so they cancel each other. So there is no net magnetic field. But if we were to put an iron piece in the influence of some external magnet, then what's going to happen is they're going to line up these, basically line up in the direction of this magnetizing field, right? So let's say I have a magnet, North Pole, South Pole, and if I bring a tiny, let's say metal here, and I put that next to it and leave that for a day or so, slowly what happens? These domains kind of line up. Or if I want to do it faster, what I can do is I can just rub it, but I have to be careful. I have to go from one side And then just like magnetic field line, I have to loop and come here and go like that. If I rub this for a while, then it quickly becomes magnetic. But we can just leave it close to it and it's going to be magnetic. It's not going to be very strong magnet, but still they're going to be magnetic. It's going to be magnetic means there is now net magnetization in a particular direction, and that particular direction is the direction of the source or the magnet you are using to magnetize this magnetic material. And these kind of materials are also called ferromagnetic materials because you can make magnet out of them. Okay, so these mostly the magnet you see in the market, they are made up of this ferromagnetic material, we say. Right? Okay, so we figured out, okay, how much, how to figure out direction of a magnetic field generated by a loop, right? Current loop, let's say current loop. So an electron orbiting also forms a current loop, or there can be many electrons orbiting or going around. That is also a loop. Or we can have a loop of wire, right? Where current is flowing actually. You connect, you make a loop and connect a battery and there's going to be current circulating. So that becomes a strong current and that's going to give us relatively stronger magnetic field. Okay. So we learn how to figure out direction by using right-hand rule. So what's the value then? So value of this magnetic field denoted by uppercase B depends on the current and how big or how wide the loop is. Okay, so radius of the loop, and that is given by this equation. And if you recall, for Coulomb's law, we wrote K Q1 Q2 over R square, and later we also used this epsilon naught, and this epsilon naught is basically related to K. And so instead of writing this, we can also write Coulomb's law, like 4 pi epsilon naught R square, something like this. So this we said, okay, this is the electric permittivity. So how easily permittivity, so how easily it can, let's say, permeate or transmit the electric field. That's what it means. In some material, what happens? The electric field, transmit better than the other kind of material. So similarly, we have this. So this, the symbol is epsilon here. This one is called epsilon. And this symbol here, probably you already know it. Did we use this in physics 1? I kind of forgot. So anyway, that's called mu and 0. So this is called, it's not permittivity, but we call it permeability. Okay, just a constant. It is just a constant, just like this epsilon naught is. Okay, so it depends on how much current is there and what's the radius. Okay, and this gives us the magnetic field at the center of the coil. Okay, so now what we can do is, if we want a stronger field, we can put several coils together, and such a structure is called solenoid. And when current is flowing through this, then it becomes a magnet, like a magnet, exactly like a magnet. But since this is not the real magnet, it is because of the flow of the current, right? In the wire, we call this electromagnet, okay? So this electromagnet, if the current was going something like, see, it is coming out, based on my drawing here, it is coming out something like this. So it's entering something like that, right? and then it's looping like this, okay? Yeah, looks like it was going something like that, and then it's coming and going something like this. So seems like here, if we look overall, this is from our side, the side, side on this coil that is closer to us. It seems like, these are uh, just coming out from this side, lower side, and going in from the upper side. So that's how the current is looping in this loop, okay? So we can use that right hand in this loop as well. You can grab the loop in the direction of current flow, and thumb points in the direction of magnetic field. And that's what these arrows I'm showing, the direction of magnetic field is that. And what's the value of magnetic field inside this solenoid? That is given by this equation, kind of similar, but not exactly. Now it has a length, so it makes more sense to write in terms of the length of this coil, and then the number of turns in the length. So the ratio of number and the length, we can write that as a, number density. So for example, if we have, let's say, 10 centimeter long, length is 10 centimeter, and let's say we have 5 loops. So how many total loops are there in 10 centimeter? Let's say 5 loops, okay, for convenience. So just 5 loops. So now, in this case, what's the density then? So we want to convert this centimeter into meter. So this becomes 0.1 meter. 10 centimeter is 0.1 meter. So if we divide this L by N, we say, okay, that's the number density. So if there are there are only 5 in 10 centimeter, then how many of them gonna be in a meter, right? So basically we divide N by the length. This is 0.1. So when I divide 5 by 0.1, this is 50. So in 1 meter, there are going to be 50 loops, right? So 50 loops per meter. So that's the number density, and we denote that by lowercase n. So the equation becomes simpler here, okay? Mu naught Ni. So it simply depends on, so basically this is the field inside the coil. So remember the MRI machine, it has this circular coil, and you go inside. So they turn on the current in that coil, and then what happens? There's going to be current flowing in the coil like that, and you are sleeping inside there. And then that's how it makes image by making use of the magnetic field there, okay? So this kind of coils are frequently used in medical devices as well, and engineering, of course, in many places. So now that was the, let's say, what is a magnetic field? Where does it originate from? And how much magnetic field a coil can produce? So those kind of things we just learned, okay? So now, what we have is this short video I grabbed from the YouTube channel. So if you have that, let's say, the PDF file that I just posted on the Canvas, so you can copy this link and paste on the YouTube or in the browser, and you can open this, or you can just watch it here. And hopefully there is sound here.
Gun and a phosphor screen. The electron gun emits a beam of electrons which travel down the tube and strike the phosphor screen, which gives out light. So the blue dot on the screen shows you where the electrons are. We accelerate the electrons through a voltage difference of 1,000 volts, and they strike the screen with a velocity of 20,000 kilometers a second. That's the distance from Christchurch to London in 1 second. Here's the magnetic field. It's just a simple lab bar magnet with an arrow drawn to indicate the direction of the North Pole. So I have field lines coming out of the North Pole, looping round and coming back into the South Pole. Now watch what happens when I bring the magnetic field close to the beam of electrons. You can see that there's a force on the electron beam downwards, and the force is at right angles both to the magnetic field and to the direction of the electrons. And if I bring the magnetic field down from the top, the electron beam is deflected to the side. And it doesn't matter what angle I bring the field, the electron beam is always deflected at right angles. So it's really important that the magnetic field is at right angles to the direction that the electrons are traveling. If I bring the field along the same direction that the electrons are traveling, you can see that there is no deflection. You only have deflection if you have magnetic field at right angles
or any other angle than the 0. Okay. So here I grab those screenshot. So here the field, magnetic field is pointing this way. Oh, I messed it up here. So this magnetic field is this way. And since the beam is coming down, so that means force must be acting this way. So yes, my bad, I labeled this incorrectly. So force must be this way. See, the field is going this way and force is down. So how do I know force is down? When magnet wasn't there, this dot was at the middle. Okay. Now the dot is down. So that means it's getting pushed. Means the force must be down. So what that means? Beam of electron means it's a moving electron. So the person said electron gone. So what you do is you heat a very thin coil of the wire, okay, conductor. And conductors, they have a lot of free electrons, right? And when you hit them, what happens? Some of the electrons leave the conductor. Just like when you boil water, what happens? Before it starts boiling, some of this starts evaporating. When it's boiling, the evaporation becomes faster. Similarly, you can think of like these electrons coming out from the wire, just like water molecules leaves the water when you are heating, okay? Similar thing happens here. And then you push that by applying the potential difference, and that's what makes the electron gone. So that is not that important. But what is important is that now you see you somehow created that moving electrons, and those moving electrons are just were coming straight at that point. But when you bring this magnet, what happens? It comes down, means there is this force acting down. So this is electron. So these are electrons. And remember, electrons have negative charge, right? So that means it's a negative charge, negatively charged. So here, this dot here means the electrons are coming out of phase, for example. Remember, cross, the notation cross means going inside the phase, okay, away from us. Dot means it's coming towards us. This is just convention, okay? And over here, just like I said, I messed up. So B is here. So here, B is in this direction and B is in that direction. So without, let's say, doing this experiment, can we predict which direction the electron's going to move? Will it go up, down, or this side or that side, right? So can we do that? Turns out we can by using right hand again, but slightly differently. Okay, slightly differently. So there is another picture as well, and I think over there I messed up. Oh, this time I did not. So force is this way. See, it's moving that way. Field is that way. So in this one, I did not mess up. Here I messed it up. Okay. So we have this. So we have to remember this rule, and I think it was in pre-class assignment as well. So you start just like before with your stretched finger and hand, but this time, rather than aiming for current for these fingers, 4 fingers, you aim that for the velocity. Okay, whatever direction it's going, you aim these 4 fingers in the direction of velocity. Okay, stretch fingers to V in the direction of B. So for example, let's suppose I have B going that way and B going that way. Then what we want to do, we start by doing this and then slowly crawl that finger this way because the B is in this direction. Okay, so it's like we are grabbing that thingy, okay, with our right hand. So first position here, the second position is there. So this is, I just overlapped 2 images together to show you, okay, it goes from there to there, okay? So the original was there, now it is there. So both of them, I'm showing that in the picture, okay? Looks a little bit creepy, but once it is here, it shouldn't be there, right? But I'm keeping that to keep that in one picture. Okay, so you crawl finger, so straight thumb gives you the direction of force. So now, let's see, can we verify these 2 images? Can you do that? And by the way, this direction is for positive charge, by the way, for positive charge. If it is negative charge, then we have to flip the direction. So you found this for positive. So you treat even the electron as a positive charge until you have this thumb, and then later you flip the thumb, okay? And so if you got this direction, then what you do is you flip for the electron. You reverse that for the electron. So if you got east for the positive charge using this rule, so this rule is for positive charge, but we can use this for the negative as well, remembering that for the negative, once we're done with the positive, assuming that's a positive charge, we just flip it, okay? We just flip it. So over here, so V is directly coming, let's say towards, let's say going towards the screen. So that means it's coming to our screen. So it's coming towards us. The dot is coming towards us, right? So dot is coming towards us. So that means we need to start our hand, these 4 fingers pointing in our direction towards us, towards our nose. Hey, touch your nose. Now these fingers, 4 fingers, are pointing in the direction of V. Okay. And then now, what is the direction of B? So B is this way. So it is towards my right. How about yours? In the picture, do you see this thing here is pointing to the right, right? So that means what you do is now you start by bringing like that and then crawls in the direction to the right. So my right is this way, okay? So that means my thumb points up. So if this was positive charge, force would be acting up. But since this is electron, we need to flip it. So it's going to be down. So that's why the force is down. So that's why this dot is moving down. Okay. So that's for that. So let's try that one, that for this one as well. So B is still towards us, right? So Now the field is going down now, okay? So field is going down, so that means I need to, point this palm down so that I can crawl in that direction. So now you see my finger is going to my left, okay? Finger is going to my left. So thumb is going to my left. So that means that is the direction of force, okay? See, without knowing which way this electron gonna move, we can tell, okay, this is the direction the electron should be moving. So did I flip this? Okay, so what went wrong here? So it was coming something like that. I went down, so actually it's still to the right. So for the electron, I need to flip. So that's why it is to the left, okay? So yes, you need to free up your hand and do the practice, okay? Without practice, it's not gonna happen. So otherwise, it's gonna be always kind of confusing. And I think for the negative charge, we need to flip it. And that's what I'm saying here. So right hand rule, assuming it's a positive charge, but we can do that for negative. For the negative, at the end, we just flip the direction, okay? That's it. So now here is a question for you. Let's see. So if you did not practice, hopefully you now practice and do it well. So you have 1 minute and 30 seconds. Take your time. Okay. So this means this is electron. Oops. This is electron and electron is moving in that direction. So on the screen, electron is moving to the right. Okay. So it says B field points into. So if I were to draw that, that's how it's going to look like. The P field is going into, means cross. Never mind this magnet here. Oh, 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So now let's see what we got here. So we are everywhere. So that means a lot of confusion. Okay. Let's see if we can do it. So now you start pointing your 4 fingers in that direction to the right. Okay, to your right. So you do like this. Orient yourself, it's pointing to the right. And then now you may have to further orient it such a way that you can actually crawl this in the direction of magnetic field. So in this case, it is going into the screen. So that means my screen is right in front of me. So that means if I do that, if I do this, that means I am crawling in the direction to the screen. So that means that's what I am doing. So my thumb is pointing up. Okay. So that would be for positive charge. Now for negative charge, I need to flip. So that means it's going to be down. So this is negative charge. So it looks like C is correct answer in this case. So did I do that right? Let's check one more time. V is to the right. And then I'm crawling this towards the screen. My screen is in front of me, so that's why it's going that way. So that way my thumb, when it's raised, it remains up. So that would be the case if that was positive charge moving, but it is negative charge moving, means I need to reverse that. Okay, so it looks like down is correct answer in this case. Okay, so couple of things you want to keep in mind. So magnetic field and force, they are always perpendicular to each other. And the force is also perpendicular to the velocity. Okay, so for example, velocity right now is going towards the right. So that means perpendicular to the right cannot be left. So if you remember that, then you will avoid choosing left. Okay, the force is always perpendicular to the V and B both. Okay, that becomes 3-dimension. So for example, let's say if I have a B going like that, and let's say electron is moving down, or let's say positive charge is moving down, then force is going to be either this way towards the screen, towards you, or towards me, perpendicular to both of them. Okay, it cannot be along the direction of B or V. Force always acts perpendicular to them. B and B can be perpendicular or could be any angle, but the F is always perpendicular, either this way or that way, and that depends on the direction of V and the charge, what kind of charge it is. Okay? So now there is another one. So this time it's a positive charge and it's moving this way, and B are like that. So there is angle between them, which is not 90 degree in this case, but force is perpendicular, or force makes 90 degree to both of these. Okay, so B is on the page, right? So this is on the screen. B is right along the page. Okay, so now with that, I'll open the poll, and you have a minute and 30 seconds. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C. Again, A cannot be the answer because see, along the B, never. Force is never along the B. So this is B. We are talking about force due to this field. So two different things we are talking about. And this FB or force due to this magnetic field on the moving charge is always perpendicular to B, means it cannot be in the direction of B or opposite to the B. It cannot. Okay. So now if you start fingers this way and crawl that way, what happens? My thumb is pointing to the screen, okay, like that. So that's why C is correct answer. This is better than the previous one. And when is no force? So in the video you saw it has to be 90 degree, but the magnetic field in B does not have to be 90 degree. It can be any angle. If it is 0, then force is going to be 0, because remember equation is QVB sine theta. Okay. So sine 0 degree is 0. So that means when B and V, they are same or opposite, means 180, sine 180 is also 0. Okay. So if the V is in the direction of B or exactly opposite, that means if V and B are parallel, then in that case, force is going to be 0. The charge does not experience force, but any other angle is going to experience force, okay? And when it does, we can figure out the direction of force and value of force using this formula, folks. So it looks like it's a good time to take a break. So let's take a break. I'll see you after break. Okay, folks, so welcome back. So I briefly talked about the value of magnetic force and wrote the formula in the last slide as well. So I'm doing the same thing here. So here, let's say we have a magnetic field lines. So by drawing a tangent line at that point, we can say, okay, that's the magnetic field direction, the strength of magnetic field or direction of magnetic field. So length means strength and the arrow means direction. So now let's suppose a charge just, flies through there. Something like this. Oh, pretty close. So B is in that direction, V is in that direction. Okay. So now in that case, we say, okay, what's the angle between them? That's theta. Okay. So the force is given by the product of this QB, and this is called cross. We don't read that as a times, cross, and this and times B. Okay, this is cross or vector product. So sometimes you may see it's written something like that. That means that's what exactly that means. Okay, but we're going to be using this simple equation like this. So this cross translate into sine theta there. Okay. Remember we had work done as a force times displacement times cosine of angle between them. Similar idea, but in that case, force and displacement both vectors, but this product is not a cross product. We called it scalar product, and that's why it is cosine theta. In that case, we put dots. Sometimes it's also called dot product. So just like we did not talk much about dot product over there, here I'll just remind you that you may see something like this as well, but we're going to be mostly using this, okay? Force due to magnetic field on a charge Q that is moving with speed V at a magnetic field B is given by this equation, where theta is angle between this V and B. If V is going something like this, then that's going to be the angle between them. Okay. If V is going something like this, that's going to be the angle between them. Okay. So this being B. So this angle between V and B, that's what that theta is. And that's how we want to read it. Force due to a magnetic field on a charge Q is equal to the charge times the magnetic field strength times the velocity times the sine of angle between velocity and the magnetic field. So that's how you want to read this. And by the way, I just recall the right-hand rule. If you took physics with me, probably we did that for the torque, angular momentum, and angular velocity as well. It's basically same thing. Over there, we crawl that in the direction of spin. Here, we crawl this into the direction of magnetic field. First starting towards the V. That's it. Okay. So now we know how to find both magnitude and direction. And by the way, this V sine theta also can be thought as a component of V. Remember, we can have a vector that can have a horizontal vertical component. So if this angle is theta and if this vector is V, then we can write this as a V cosine theta because this is adjacent and this is V sine theta. Similarly, this line here is opposite. So that's why this is perpendicular component. So we can think of, okay, perpendicular with respect to what? Okay, so this is parallel to the B magnetic field, and this is perpendicular to this. So you go in the direction of magnetic field, and then you go perpendicular to it until you reaches to the tip of that. So from this triangle, we can see this is going to be the sine component. So in this case, when B is exactly perpendicular to B, so for example, this is B and B is something like this, exactly perpendicular means theta is 90 degree. You know, sine 90 is 1. So basically, this becomes just QVB. But it's not always QVB. It is a special case. It is true only when this V is perpendicular to B. Okay, so that's why this notation there. So this is the value of the force when V and B are perpendicular or when angle between them is 90 degree. So that's what I'm emphasizing here. So from this equation, we can tell this FB gonna be 0. When V is 0, that means if there is a charge, but this charge is not moving, then it's not gonna experience force, okay? So there can be electric field even when charge is not moving. But if charge is not moving, it does not produce the field, it does not experience force when you put that in the field. And of course, when B and B are parallel to each other or anti-parallel, so that means theta is 0 or 180 degree. Looks like I did not write it, but kind of same. So what is the unit of B? So electric field, we said was Newton per Coulomb, right? So electric field, what's the unit of electric field? Let's say 10 Newton per Coulomb. That's what we wrote. And how did we figure that out? By using the definition of electric field, which is force divided by charge. So that's how we figured. But the B has this kind of equation. So force per unit charge, but there is velocity as well. So let's write B, solve B. So we are just finding the unit, and this sine theta does not have unit. We don't need to worry about it while finding the unit only. So I am just rewriting this equation for B by solving for B. So B is here. So that means this Q gonna go in the denominator, B gonna go in the denominator, and that's what I'm doing. So that means this is force, this is charge, right? And this is velocity. So now let's do slight reorientation rather than in terms of charge. Let's write in terms of current, and that we can find by writing this velocity as a displacement divided by time, or distance divided by time if you are just looking for the unit. Direction does not matter for the unit. So velocity, I wrote that as a distance over time. So now you can combine this charge and time. Charge divided by time is current. So that's going to be unit of current, which is ampere. Unit of force is Newton, and unit of distance is meter. Okay, so that means unit of B or magnetic field is Newton divided by ampere times meter. But it is called Tesla. The name of that car, Tesla, came from this name. It uses coil in the motor. Okay, so for example, here is a problem related to this. Okay, let's see if we can do that. So what happens is sun is a kind of ball of fire where what's burning? Hydrogen is burning. And that is constantly converting into helium. And in that process, it also ejects. So it has large magnetic field as well, actually. Sun has a large magnetic field, way larger than our Earth's magnetic field. Earth's magnetic field strength is about this. It is given here. So it ejects a lot of these charged particle. So they go all around this space, but some of them also comes towards the earth. Okay, and that's what it is talking about. Let's suppose a proton is moving with that speed. See how fast it is? Way faster than the plane. Way faster than the plane. It is perpendicular to the Earth's magnetic field. And magnetic field of the Earth is parallel. So what happens is it comes from the North Pole, goes to a South Pole, and if you are near equator, it's totally flat. Okay. So Earth's surface is here, magnetic field are just going something like that. Okay. And that's what it is talking about. What is the force on the proton due to the field if the field strength is that much? So this is B. B is given here. Okay. This is V. V is given, but it is in kilometer per second. We need that in meter per second. Okay. And we are given angle between V and B. It says perpendicular means that's 90 degree. So let's suppose this is the V. Okay. The protons are coming. And there is Earth with its magnetic field. Okay. So it's coming from the top over there. So it's falling on the surface of the Earth. So this, I just try to orient picture I found. Okay. So that way the field and this B, they are perpendicular to each other. So they are making 90 degree. That's what it is saying. Okay. So B is pointing down and B is going left to right in this diagram. Okay. I think I drew another big line to make it more visible. Okay. It is like one of these lines here, you see. So Earth behaves like a magnet actually. Okay. So it's basically generating the, we can say, okay, there is magnetic field lines. So North Pole of the Earth, so-called Earth magnet, is not real magnet there, but it is behaving as if there is a magnet, okay? So that is kind of on the south geographic pole, okay? So north geographic pole, this is south geographic pole. Oh, magnetic North Pole supposed to be South Pole here. So that's why these are entering there, okay? Yeah. there is another mistake here. Magnetic South Pole and geographic North Pole. They are kind of totally opposite. Why we call this north geographic north? Because when we bring a compass, remember the compass is tiny magnet, and north pole of the compass gets attracted towards the south of the Earth's magnet. So that's why it's pointing in that direction. And we thought, okay, that's the north. But turns out, for the magnet purpose, it's the south magnetic pole there at the north geographic pole. They don't overlap each other. They make certain angle between them, Earth geographic north pole and magnetic. Okay, it's kind of turning, and it's kind of gradually increasing. The observation shows with the time, and the evidence shows that that thing keeps changing direction. Actually, keeps flipping in few million years, few 100 million years. So anyway, for our lifetime, it just remains constant. So that's what we are saying. Okay. So now we have all these, and it's asking us to find what is the force. So we need to find value and direction of this force. Okay. So V is 820 kilometer per second. Ooh, there are 1,000 meters in a kilometer. So 820 times 1,000 meters, and this is already second, so we don't need to convert that. And magnetic field strength is 5.0 times 10 to the power negative 5 Tesla, and it is down, vertically down. Okay. So the now question is, force is what? So that means value and direction. Remember, force is a vector, so that means we need to calculate both. It did not say just find the value or direction. So that means when it says just force, we need both. We need to calculate both. Okay. So let's calculate value. So the angle between them is not zero, but 90 degree, right? Just like I said. The V is vertical and B is flat. So that's 90 degree. So normal. Okay. So F is what? So F is Q V B sine theta. What is Q? Q is proton. That means proton has a charge, positive E, which is 1.6 times 10 to the power negative 19 coulomb. Okay. So now we can plug in all these. And get some ugly numbers here. 820 10 to the power 3 or 8.2 10 to the power 5 I should write. Let's write that. 8.2 times 10 to the power 5. That's what that means. 3 zeros here, and there is 1 0. And when I bring this decimal here, it's going to count 2 zeros here, 3 and 2, 5 zeros. We are moving this, right? So that's that. And then B is 5 times 10 to the power negative 5. Oh, how convenient. This is 10 to the power 5. This is 10 to the power negative 5. And then sine 90 degree, which is positive 1. So that means it is just, okay, this goes 16 times 5 is 80. 8 and 8 times 8 is 64. And there is 2. So 65, something like that. Okay. Close to that. and 10 to the power negative 19. So if I write 6 point, you guys want to use calculator, okay? Yeah. So it's going to be small number. So force is very small. But remember, although the force is very small, mass of proton, they are very small as well. Mass of proton is in the order of 10 to the power negative 31 kilogram. So even this tiny, tiny force can accelerate it a lot, okay? So they are accelerating a lot, okay? Okay, someone got the number and it is for everyone. So yeah, that sounds reasonable, okay? So that is the value of force. Now, how do we find the direction? For direction, right-hand rule, and these goes in what direction, folks? V. So which way is V? Down. So go down like that. Okay. And then now, see this is going geographic north. So you need to, you let me make this a little bigger here. So let me on share and later remind me to share. Okay. So, oh, what happened? I did not on share. Okay. So now you can see a bit bigger. So you want to go like that down, right? And then now, do you know which way is the north in your place? So download compass in your phone and figure that out, okay? But I know which way is north for me. So it's going something like that. So looks like my thumb is going. So thumb basically gives you the force. You crawl towards the B, okay? So I see there is a direct message that says, I thought our thumb go towards B. No, thumb gives you force. B and B is handled by these four fingers. You start with the V and then crawl in the direction of B. So in this case, you start down and then crawl towards the north. Now thumb goes to the east, means the direction of force is to the east. So these protons are feeling or experiencing force to the east. Okay, so that's how we find it. Okay, now let me share back. Direction is to the west. See here, there was real physical direction down. So that way we were able to figure out real physical direction. Okay. Did you figure that out? Do you want to try? Go ahead. I think I have another sketch as well. Okay. So here I am showing you that. There. Yeah, I cannot sketch hand and fingers. So I sketch this one here. So you start finger down and then crawl them towards the north because the B is going to the north here. Okay. And then now your thumb points. Let's see, in this case, which way thumb should point? So finger goes there, and that way means looks like it's going to be coming out. Hold on, hold on, hold on. Yeah, it's going to be coming out. So let's say, although we don't use that for force, I'm just using that notation. So it's like on the screen, it would be just coming out towards us. Okay. But here we have real physical direction. So we need that in terms of real physical direction. Okay. So do we move on? from here. Okay. So the direction is to the west, not east. So did I say west? So are you saying based on this north here? See, east and west could be any direction, say over here. So we cannot just say east and west based on just this, but you have to actually do it physical direction here. And looks like when we do that and turn that to the north, my finger points to the east. Okay, my thumb points to the east. So it is east. If I said west sometimes, I don't know. I don't remember saying that. If that's the case, then that's, I made mistake. It's east I've been saying, I think. Okay. So now, here, motion of charged particle, but here we are assuming that the angle between B and B are perpendicular. Means 90 degree, not any other angle between B and B, but perpendicular. So what's happening here? This dot means these fields are coming out. See, you are looking at the tip of the arrow. So arrows are coming out from the paper or the screen, okay? So now this is V, and by the way, this is negative charge in this case, but could be positive charge as well. Direction of force is going to be exactly opposite. So this negative charge here moving in magnetic field, okay? So it was, let's say somehow it was, pushed that way, but it's not going to move straight because it experienced force. That means it's going to change direction. And since force is always perpendicular to B and B, what happens? That this charge is going to move in circle. Remember circular motion? When force is perpendicular, object moves in a circle. Here, force is tension. So tension force is towards the center of the circle, right? See here? So similar idea here. It's like a mass here. Going in circle means the force must be towards the center. But can we verify that? So for this configuration, yes. So I start by pointing my fingers to the right on the screen, and my B are coming out, okay? So that means I crawl them up because B are coming out of the screen means I crawl them up. So my thumb is pointing away. I mean, my thumb is pointing this way. So thumb is going this way, my thumb. But since this is negative charge, I need to flip it. So that's why the force is that way. So if this was positive, then force would be this way, and this would be moving in this kind of circle. Okay. So it goes in a circle, and let's say the radius of the circle is that. So that means it's a motion in circle, circular motion. And how do we use Newton's second law for circular motion? Sum of forces in radial direction is equal to mass times acceleration in that direction, right? So force in that direction means acceleration is also in that direction. So we use this in circular motion in physics 1. So we are using this idea here. So in this case, only force is this force. So net force can be simply written as this force due to magnetic field, or FB, just that. And we learned that that is QVB sine theta. So that's what I'm writing here, theta being 90 degree, okay? So I'm doing that. Mass And when something is going in circle, its value of the acceleration or radial acceleration is given by b square over r. And this is also called centripetal acceleration. But we mostly said this is radial, okay? So that's what I'm using. So you can see there is b square, but there is b, this is same b. So that cancels. So giving me, and sine 90 is positive 1. So that gives me this. So now this is the relationship between what quantities? Charge of the charge that's moving, and this is the speed of the charge, and this is radius of the circle, this is mass of the charge that's moving, and this is strength of the field. So if we know, like there are 5 of them, if we know 4 of them, then we should be able to solve for 5th one. Okay, so that's what it is saying. So before we do problem, here is one use called mass spectrometer. Oh, I did not write. See, I didn't write the name title of the slide. Mass spectrometer. So see the same equation I'm writing. So this mass spectrometer uses this. So I see there is a question in the direct message. How is B up in the previous slide? See, B is field we can apply. So whenever you see dots, that means it's coming up in that direction. It's coming towards you. So it's like we are applying that field. So we are putting a magnet, let's say, so that the north or the field lines are coming something like that. Okay. So it is a setup. So B comes from that setup. And notation for this thing coming out of the screen is dot inside a circle, or could be just dot. Okay. And if you see cross, that means it's going inside. So this B field is given for you. Okay. B field did not come from anywhere. Force came. So force and B field, they are not same. Force and field, they are not same. Keep that in mind. So if charge moves in a field, it experiences force. So force is F, and the value is BQB sine theta. That's the value force. See, this is force, and it is field. So these are the field denoted by these dots. Means there is field everywhere. Okay? And the value of that field is B, we are saying, and direction is coming up. So that's what this diagram means. So that's how we need to read. And there is similar diagram here. There are these little dots. That means they are coming up as well. Yeah, usually it would be like circle and dot when it's nicely done. But when it's done by me, some sloppy work, you may also see something like this sometimes when I'm in rush. Okay, so now you sort electrons with certain speed. Let's say charges, I should say charges rather than electron. Here, this mass spectrometer means it helps us to find the mass of the charges. Let's suppose you have different kind of charges and you want to figure out which has larger charge, okay? Which has larger mass, I should say. Then what you can do is you can shoot those charges in a magnetic field and they're going to go in a circle, okay? Now, if I'm solving this for mass, this equation going to be this, right? So I'm solving this. So R going to go multiply, B going to come here and divide. So that's what it is doing. So charge has a fixed value. We are shooting a charge. A charge is moving, means like we can say, okay, it has a value. And it is moving in a magnetic field, given magnetic field, or the field we set up by putting magnets. So B is known. And since we are shooting, let's say we know what speed the gun is shooting, let's say. If we know all those, then what we can do is by looking at this path or the radius, we can measure the radius of the circle. Okay, with the circular path, we can measure. So in the experiment, what do? You shoot the electrons and they go in circular path, and you measure the radius of the circular path. Okay, and you cannot see electrons. Remember in that video we saw there was that dot, blue dot. So that was from the fluorescent. So electron comes and hits and it excites the light, and that's how we get the fluorescent light bulb. So basically same idea. You have to let these move in some sort of gas so that the gas gets excited and emits the electron. So anyway, let's say there is device where you can see the path. So once you have path, you can measure the radius. So now with this radius, you can calculate mass. And from this equation, you can say the mass is directly proportional to the radius for a given charge for one setup of experiment, right? So let's say you shot this, like similarly charged two object and you found two. So this one outer one that has a larger radius, right? So outer has a larger radius than the inner one, of course. So that means larger R means it has a larger mass. Mass and R, they are proportional. So larger mass requires larger force to quickly turn, right? Otherwise, it just wants to fly out, but there is a force. So because of that, it slowly turns around. So that's why it goes in larger radius. Larger mass, larger inertia means it goes through larger radius. Okay, just like when you are turning a truck versus a car, turning a truck takes larger radius, kind of something like this. Okay, so anyway, so we can have a for example device. So this device uses or accelerates the charge, okay, and then hits the target, and then excites some sort of radiation, and that radiation is captured to get the image. Just like for our photograph, what happens? Light hits our body, gets reflected, that goes in the camera, and camera captures that, and that's how it makes me image, right? If we were to in complete dark, then camera not gonna give you image, because to image or to see something, the object has to be reflecting the light. Okay, so similarly, this one also excites some sort of radiation like light. Could be visible kind of light or invisible kind of light. There are visible and invisible lights. We'll talk about that a little later. But anyway, so I have done the same problem in the note as well. Okay. So here the charge of proton is given, mass of proton is given, right? So let's say that's a charge of proton that is given, and mass of proton is given. So those numbers are those. And then required kinetic energy of proton before it leaves the cyclotron. So yes, so we want it to be moving with certain speed so that it has a certain amount of kinetic energy. So kinetic energy, K of proton is half mass of protons times speed of proton squared, kinetic energy, half mv squared. Does that sound familiar to you folks? Okay. Okay, so that's the kinetic energy, and that is given. The whole thing is given. Okay, so 1.76 times 10 to the power negative 12 joules. So since mass is separately given, or we can tell, so that means speed is given. You can tell. Okay, so with kinetic energy, we can figure out speed. So let's find speed. Oh, part A is velocity. So using this, so half m mass times velocity of proton square is kinetic energy. So that means velocity proton squared is 2 times kinetic energy. 2 is in denominator, so it goes to the numerator. And mass of proton, okay? So that means velocity of proton is 2k. K is kinetic energy over mass of proton. So that means we get velocity here, okay? Kinetic energy is known, mass is known, although those numbers are ugly. We know both of those. And this is done in note. So verify those numbers by punching in the calculator when you have time. And if there is mistake, let me know. Okay. B, what is the radius of proton circular path? So that means R is what? Okay. So just like here in the previous slide, see it was short with certain velocity. So if you know V, then you should be able to tell radius. You can calculate radius. Okay. And by the way, B is given here 1.2 Tesla. That's a strong magnetic field actually. So since it is moving, so I don't remember that formula, okay? Now that may be in formula sheet, but I don't remember. So what I do is I always, whenever I see this is moving in circle, means sum of forces is mass times acceleration in that direction. So that means QVB sine 90 degree is mass of proton, and this is charge of proton, by the way. We are talking object is proton here. Mass and the velocity proton is squared, and this velocity is also velocity of proton over the radius. So we want to solve for radius. So basically it is same equation we had. So before we solve for mass, here we are solving for radius. So this Q and B just comes down here. And that's what you see here as well. Q, P, V, P, B. Oh, one velocity goes away. So B and sine 90 is that. Did I miss something here? QB cross B sine 90. So how come there was, yeah, there was just Q and B, there was no B. Okay, so there is no B. So Q and B, and this is mass V proton over R. So R is MPVP over Q, P, and B. Okay, just rearranging this for R, solving for R, we get this. So you plug in these numbers and get the answer. Okay. So since you are putting everything in SI units, so it should be in meters. So that's how we do it, folks. So that's how we use circular motion concept. See what we learn in physics 1, we are using all of those here. Okay. Okay, so I got a huge number for V. Yes, it is moving. These things are moving really fast. Okay. But shouldn't be faster than, if those numbers are realistic, shouldn't be faster than the speed of light, which is 3 times 10 to the power 8 meter per second. Usually speed of these protons are in the order of 10 to the power 6. So if you are somewhere there, should be fine. Okay, but it is done in the note as well. Okay, check that. So it is 51. So I have to let you go, folks. So we're gonna pick up from this aurora borealis next class. So theory we already learned, but this colorful display of light is because of these charged particle spiraling. So we'll start from this slide next class.
I have a